In the last lesson, we learned how to use moles to relate the number of particles that we have to how much it weighs. And we're going to do the same thing today, except we're not just going to talk about individual atoms. We're going to talk about molecules and compounds and how we're going to use the mole to describe them. So we know that 1 mole is equal to Avogadro's number of atoms. But it can also be, if we're talking about something that's a molecule like water, that can also be 1 mole is equal to that many molecules of water. Or if we're talking about something that's an ionic compound, we'll get to what that means a little bit later. We represent those in formula units. So 1 mole of a compound is going to equal Avogadro's number of formula units. Now, just like last time, 1 mole of anything going away its average atomic mass in grams. So previously we talked about elements. We just looked for that number on the periodic table and recognized that that would mean 1 mole of that element weighs that number of grams. So over here, I put the molecule water on the board. Very important one. Use it all the time. We made up a lot of it. The atoms are chemically bound, and with this, there's a beginning and an end to the molecule, which makes it different than an ionic compound, which we're going to talk about in a couple minutes. So calculating the average atomic mass for a molecule is still pretty easy. All you got to do is look on the periodic table, same way you did before, and you multiply the average atomic mass by the number of atoms. And that'll give you the mass of that element. And then you do that for all the different elements in the compound. For water, it's just hydrogen, oxygen. So you multiply oxygen's molar mass by 1, 16. So your 2 from hydrogen and your 16 from oxygen give you the 18 grams, which is what 1 mole of water weighs. Now, if I ask you how much 3 moles of water would weigh, all you got to do is use that as a conversion factor, just like before. So 3 moles of water, 18 grams of 1 mole, you multiply that out, you get 54 grams of water. The other way we could go with this is I could ask you how many molecules would be present there. So now we just use Avogadro's number the same way as we did before, except instead of atoms, you put molecules. And that'll give us the answer. And that would be 1.806 times 10 to the 24th molecules. Now the only different thing I can ask you with this type of problem would be, how many atoms would there be of a given element? So I ask you how many atoms of hydrogen there would be. I don't know why the hydrogen auto race, but here it is. How many atoms of hydrogen there would be in that many molecules of water. And if you look at the molecule, you clearly got 2 hydrogens for every molecule. So all we do, have the number of molecules here, you multiply it by the number of atoms of hydrogen in that molecule, and we get our answer, which is 3.6 times 10 to the 24th. Now, when we look at an ionic compound, it's different than a molecule because there's really no beginning or end within the crystal lattice. And we call a formula unit really the lowest whole number ratio of the ions in that compound. So like sodium chloride, for example, is just alternating sodium and chloride. It goes on for a long, long time. More atoms than you can count to in your whole lifetime in a single cube of salt. So the lowest ratio there is 1 to 1. So we would call this sodium chloride NaCl. I put a more challenging one on the board so that way we could look at the different possibilities you might encounter when you describe an ionic compound. So molecules are between only nonmetals, and ionic compounds are between a metal and a nonmetal, or cation and an anion. Calculating the molar mass for these things is just the same. When we're looking at this formula, what this tells us is that for every 3 ions of calcium, you've got 2 ions of phosphate, which each ion of phosphate contains a phosphorus atom and 4 oxygen atoms bonded together. So if I have 2 of them, that means that I have, in this whole collection, I would have 2 atoms of phosphorus and I would have 8 atoms of oxygen represented in this. So, calculating the molar mass, you multiply the number from the periodic table by how many you got. So I do that for calcium, I get 120. I do that for phosphorus, I get 62. And I do that for oxygen, and I'll get 128. All that would add up to 310 grams for every mole of this compound. So if I ask you, how much would 2 moles of that weigh? You do the same exact process. You just put the number of moles you got, multiply it by how many grams there would be per mole, and that'll give you an answer. The other way I could go again is ask you how many formula units. And you treat it the same way you would atoms and molecules. So I would ask you how many formula units would be present in 2 moles of that substance. You do the same thing. You multiply it by Avogadro's number, divide by the number of moles, moles will cancel out, and you know how many formula units you would have of that substance. Now the only other thing I might ask, which is what I did for the previous one, but I want you to do this one, is I want you to figure out, if you have that many formula units of calcium phosphate, tell me how many atoms of both calcium, phosphorus and oxygen would be present in that.